Okay, so now we would like to discuss integration, and basically we are going to need to know how to integrate in a Lorentz invariant way. So our discussion of integration, we're going to deal with two topics. So the first thing that we're going to do is we're going to ask, how does the integration measure transform? And the key word here is Jacobian. So the integration measure transforms according to a quantity known as the Jacobian. The second thing that we're going to want to discuss is the Dirac delta function. That's an extremely important concept in physics, and we'll be making a lot of use of it. So let's start off by discussing integration. So I want to integrate over R2, two-dimensional real space. So what space do I have in mind? Well, let me just draw a set of two axes. So here is y, here is x, and I might want to study the integral of the f of x comma y dx dy. And it's this dx dy here that is called the integration measure. And I'd like to discuss that integration measure. Now, there's a whole theory in mathematics devoted to integration measures, and there are formal objects that are called sigma algebras. We're not going to need to go into so much detail at all. We're going to deal with things in a much more pedestrian way. So what is the idea? Well, the idea is we start off and we break up the plane into little segments, little squares, okay? So we could imagine, here we go, I'm going to be breaking up my plane. Each of these dashed lines is some partition of the plane. I'm breaking the plane up into little pieces. And then what I can do, I can study any given little piece, okay? So let's say, for example, I'm going to study this little piece that's sitting over here that I've colored in green. And what the integration measure would do, it would give me an area associated to this little green box, okay? Now, this actually looks like a square. Let's say the width of the square is dx, and the height of the square is dy, then the area associated to that little square would just be dx dy. And that's what I mean by the integration measure. It's just dx dy, which is the area of this little square. But you know, this is not the only way to break the plane up. I could also imagine doing the following. So let's imagine that I'm going to consider some point, okay? So here's my point. I'm not going to consider its x and y coordinates. I'm going to imagine that it is at some distance r from the origin and at some angle theta. So I would like to know now, if I take a little block, what's the area of that little block going to be? And I'm going to divide up the plane as follows. So I'm going to start to divide up the plane into little segments. Each of these little segments is going to subtend a little angle, d theta. Sorry, my drawing's not very good. But each of these are d theta. And I'm going to imagine there are many, many of these regions. And then I'm going to start slicing so that this is all at some, the circular points are all at some fixed radius from the origin, so that this is a length dr, that length again would be dr, and so on. And now what I'm going to want to do in exactly the same way that I assigned an area to this square up here, I now want to assign an area to each little square sitting over here, okay? So if I want to study that square, the length of this side over here, well, that's just dr, okay? And now I need to know what is the length of this side over here. Well, for the length of that side, so let me just draw a little figure over here. What we've got is this distance over here is r, so that's the distance from the origin, and this angle over here is d theta. Now, if you remember your formula for arc length, it means that this length over here will just be r times by d theta. So this length is r d theta. So now, before the area was dx dy, now the area is going to be r d theta. That's the one length of the one side, and then the other side has got a length of dr. So if you want to work in these coordinates, r and theta, your integral, you'd take an integral of f. Instead of using x and y, we'll use r and theta. But now the integration measure, so the area that we assign to each little block, will be r dr d theta. That's the area. So you can see this is not an integral of f dr d theta. It's an integral of f r dr d theta. Okay, and I've argued very clearly for why we need that extra r sitting there just by looking at a little square on the plane. Now, we want a mathematical rule that's going to tell us what this measure is. And that's where the Jacobian comes in. So I'm just going to state the rule now for you. Let's imagine that we start with an integral, the f of x and y, dx dy, and we would like to rewrite this into an integral of f. Let's say we're going to use new coordinates, du dv, u and v. We want to integrate du dv. And what we need to have here, so let me just erase this. What we need to have here is something called the Jacobian, J. So J is the Jacobian. So the integration measure, dx dy, has turned into the Jacobian times by du dv. And what is the Jacobian given by? Well, it's the determinant of, we will have, so let's imagine here that we know that u is equal to some function of x and y, v is equal to some function of x and y. And if this is a good change of variables, then we can also write x is some function of u and v, and y is equal to some function of u and v. So let's imagine that we know this coordinate transformation. Given u and v, we can work out x and y, and given x and y, we can work out u and v. What the Jacobian is, it is given by dx du, dx dv, dy, du, dy, dv. So you calculate that determinant, and after you've calculated the determinant, you take the absolute value, okay? So you would calculate the determinant and then take the absolute value. That'll give you the Jacobian, okay? So just so that there's no confusion, this is the absolute value of the determinant. And that's the rule that tells you how does the measure of the integral transform. Dx dy will be equal to j du dv.